We started out with this schematic that came from South America, and we're working through it stage by stage. And right now we're up to the Class E final stage. After this we go into the series modulator that's down below the Class E stage. But we're going to look at the Class E stage in this video. Now, at National Semiconductor, there used to be this guy, Bob Pease, and he used to say things like, "What's all this Class E business anyway?" Okay? And I was working for a company that was similar to National at the time, Analog Devices, during the late 90s. And at Analog, I was an applications engineer, and we all were kind of supporting and helping and doing data sheets and application notes and reference designs, evaluation boards, that kind of things, all to serve the designers that were actually building the chips. So there were some really wonderful IEEE courses that were put out in the late 90s. It was the golden age of RF design after the Bell system got broken up and all of the cellular revolution took off. We basically were going crazy with RF design. So the IEEE had these series that they were sponsoring down at a Raytheon plant, I think in Lexington. And the particular ones that I attended concerned spread spectrum technology, and the speaker was Robert Price. He's the one that brought Hedy Lamarr into the world and put her together with the spread spectrum technology for the first time in the early 90s. And another one was going to be on the higher classes of amplification, Class E, D, F, and so on. And the guest speaker for the every week we would be going, so once a week thing for several weeks, was Nathan Sokol. Nathan Sokol himself was a amateur radio operator, WA1HQC, living down in that area of Massachusetts, and he was doing this IEEE class on the amplification patents that he did back in the 70s, and it finally had caught up to industry by the mid-90s. Hams started to deal with it in the 90s as well. Now, the 1990s were the infancy of the pulse duration modulation revolution, really, that took over in the AM community. People like WA1QIX was doing the initial work with tube-type circuits. Harris, of course, Harris broadcast transmitters had been in production for quite a while with PDM, but it was starting to work its way into ham circles. And it would take probably 20 or 30 years before regular Class E type modules and kits would come on the scene. Well, anyway, Professor Sokol, MIT graduate, patent holder of Class E and many other patents, was teaching the class, and I got to meet him and interact with him, along with all of these young, hot RF designers that were at the peak of their creativity at the time in the 90s. This was our textbook here, written by Goyal, and this was from 1995, and this brings some of these high efficiency techniques into integrated circuits. And CMOS and FETs and everything else were really taking off in the chips at this time. So just a little short story of my experience with Class E. I did nothing with it. 30 years go by, I did nothing with it. And here we are, and I'm finally putting my feet in the water and doing a Class E stage for the first time. It's absolutely crazy. So unfortunately, WA1HQC, Nate Sokol, did pass away in 2016. So here we are sometime later, and I'm starting an adventure into Class E amplification. I hope you enjoy this video. We'll get through this stage, and then we will go down to the modulator. So I'm laying out some parts for our junk box Class E 75 meter final amplifier. And I just wanted to let you guys know that We're not trying to build a kilowatt amplifier here. We're only trying to make 10 or 15 watts of RF, so we don't have to have gigantic components, components that you would have in a 100 or a 200 watt radio. I think we can get away with fairly small inductors. If you do want to wind your own, just some ordinary number 14 wire. You can make all the inductors with this kind of idea, just winding this on a 1-inch form or a 1/2-inch form. We can make the inductances we need. If you like to use toroids, I'm going to start out with the 1/2-inch size and work up to the 1-inch size and see if we get any efficiency differences. But the yellow cores, of course, are not preferred for this low of a frequency, but they are usable. You just need to put a few more turns on. The red core, the number 2 material, instead of the number 6, is preferred for the 75 meter band. If we do need to do any wideband transformation, of course we can use number 43 or even number 61 and make transformers with the ferrite. This is ferrite, and of course this is powdered iron. Also, devices. Remember, we're stealing devices out of ATX power supplies. The modern supplies do use MOSFETs, but some of these older AT and ATX supplies are still relying on bipolar transistors. Now, a bipolar transistor switch is still a very, very good switch, and we could use a bipolar transistor in the Class E final, just like we can use a MOSFET in the final. We've found that today you're getting better efficiencies using MOSFETs, and pretty much the entire design industry has gone over to MOSFETs. And I'm not just talking about RF, I'm talking about switch mode power supplies, Class D audio amplifiers and such. These are all using MOSFETs today, whereas high-speed switching bipolar power transistors were used from probably the 70s up through the mid-2000s. And we are going to try a bipolar transistor out of an ATX power supply. Let's see if we can get Class E with bipolar. So let's take a look at the circuit very simply. First of all, we know we have a driver. The driver has a transformer in the output to give us isolation, because we know we're going to be operating the RF stage on top of the modulator. So they're going to be sharing 30 volts. We're going to be giving 15 volts hopefully to the switch for the RF, and 15 volts for the switch for the audio chopping. So I'm just going to use 15 volts as the power supply voltage for this test circuit. Also, I've got a grid leak and some protection on the input for the gate. This is probably a 15 to 18 volt Zener, and this is probably a 1K resistor and just a coupling capacitor, like a 0.1. We do need a choke in the drain circuit. We can make a nice little 1 millihenry choke. In the Class E design, which we will go over in detail, it looks like we need about 850 picofarads to delay the voltage to current peak so that they're not at the same time, thus reducing the dissipation. 1000 picofarad coupling cap, and a 2 microhenry choke. A 2 microhenry coil. You can make a 2 microhenry coil out of almost anything. It could be a air wound coil. It could be a toroid of some kind. You can figure out something there. We'll try both and see if we get any efficiency differences. Now, the ideal load to get the Class E calculated out to be between 10 and 12 ohms. We need to get up to 50 ohms. There's two ways to do that. The first way would be to simply use a 1-to-4 on-on. That's going to take this low impedance up to 50 ohms. I like this idea because it's fairly broad band, And no matter what happens out here, it's going to transform it 4 times lower here, thus providing very good stability for the Class E stage and keeping the efficiency up. However, if you do want to do it in the harmonic filter section, which is completely separate, remember, this is not going to give you much rejection on harmonics. It's going to give you the efficiency, but you're going to have harmonics that could be down, 10, 12 dB. We need to get them down 50 or 60 dB. So we're going to have to use a harmonic filter, 50 ohms in, 50 ohms out. However, I could take these two components and do an L match and take the 10 to 12 ohms and bring it up to 50 ohms with this first section, also providing some low-pass filtering, and then this section remains 50 ohms. Or I could do it all in stages. I could go from 10 ohms to 30 ohms to 50 ohms. So there's a lot of flexibility here, and I wouldn't need to use a balun. I could do it all just with this section here using matching techniques, LC matching techniques. But I do like the idea of using the broadband balun because it's going to add stability to the stage. So we would end up with this circuit with this tacked onto the end to give us the harmonic rejection. So are we ready to start talking about Class E circuits and stages? Here's the diagram that you're going to see in all the literature, online, and so on. Basically, you're driving it with a square wave. You have this interesting output network. There's some online calculators. You put in the numbers, you get the answers, and you build the stage. Now, I'm not particularly interested in high efficiency with this project, but I know that if I get high efficiency, I'm building the circuit correctly. So that's kind of the way I'm looking at it. And I'm not going to bore you guys with a bunch of integrals and formulas. We're just going to get down to building things. But I did want to talk about some foundational material before we move on. Let's talk about the device that we're using as a switch in the Class E amplifier. Remember, it's that same device, whether it's a it's a bipolar transistor or a MOSFET or a hemped device, MOSFET. These are all devices that we're using as a switch. But of course, traditionally, we've been using them as linear amplifiers. And we know that in Class A, we're always drawing current. So that's the least efficient. As we work into Class B, we're right on the conduction angle of full conduction. We get a little more efficiency. Class AB is a little less than Class B because we've got some conduction going all the time. When we go to Class C, we've cut down our conduction angle a lot and we start to really pick up some efficiency. With Class C, it's pretty much understood that we can hit close to 80% efficiency. Class D is the first of the true switching type power amplifier topologies, and we're switching right on the 180 line, and the device is either off or it's on. Theoretically, you could get 100% efficiency with something like that, but of course devices are not perfect. Parts in your amplifier are not perfect. There's saturation voltages and other things that cause this to not actually hit 100%. So I think you could probably get close to 90% with a Class D amplifier, maybe a little bit more. With Class E, we do some interesting things with the phasing method of moving the current that you draw away from the voltage so that they're not close to each other. Remember, you have to have current and voltage to have power wasted in this case. If we're using current and voltage to produce signal, that's good. That's putting stuff into the load. But if we're using current and voltage and it's not producing any signal, that's waste, and that affects our efficiency. Also, I've drawn this in a funny way to show that SOCO recommends that you use a trapezoidal drive system on Class E, not a square wave. Isn't that interesting? So let's look at current versus voltage in the switch device. And you guys are used to looking at these for Class A and Class B amplifiers, Class A/B amplifiers. Class C, of course, the conduction angle is less. You've got very few places where you have current and voltage, current and voltage, current and voltage that represent wasted power. You just got these two little places with Class C. Therefore, the efficiency goes up probably close to 80% for a well-designed Class C stage. Now here in Class D, we're trying to get the switch to be on and off, so it's never at a point where the current and the voltage are both above the zero line. And this is kind of what we get on the output. The pulses out of the Class D light up the tuned circuit, and out comes the power. Practically, Class D can hit 90%, maybe a little bit more. When we get to Class E and we start to do some phase shifting, we can get even further into the 90s, and that's going to be really interesting. So here's the idealized waveforms for the Class E stage. As you can see, everything's wonderful. It's either off or on, and we get the filtered output. This is the ideal for the Class E right here. So this is what it really looks like in a realistic amplifier. The drive, again, is not a perfect square wave, and it's certainly not occupying the entire, and it is kind of shaped like a trapezoid. And here's the pulses that we get out. This is a realistic waveform where we've separated the switch's current from the switch's voltage. Therefore, there's no place where those waveforms are both conducting at the same time, thus wasting power. And remember, it's the current pulses into the tuned circuit that are causing the power to actually be formed and go out to the load. So anyway, the Class E trick is phase shifting. We're phase shifting the voltage so it's later and doesn't coincide with the current pulse. So basically we are juggling energy from L to C, L to C, L to C, and these two components are simply a resonant circuit and an optimum load that allow the L to C to be exactly at the right place. So that's why you need all of these devices in order to make a good Class E stage. So we're used to looking at these various circuits, and like a Class D is always shown as a push-pull amplifier, and a Class E amplifier is generally always shown as a single-ended amplifier. But in reality, it has very little to do with the actual circuit or topology. You can have different classes and have different topologies, and they're both useful. Class A or AB push-pull amplifier, you're used to seeing this. This would be like typical linear amplifiers used for single sideband and other higher order modulations. The Class B amplifier, this should all be familiar. Those are popular certainly for audio amplifiers and for some linear amplifiers. Class C, the conduction angle is cut down, and usually for RF service we use a tuned circuit on the output, but we don't have to. We can take a little bit of an efficiency hit and do Class C with broadband transformers, but someplace you're going to have a tuned circuit with Class C. Now with Class D, we send a square wave into the tuned circuit and we get out the pure waveform after filtering. Again, we're changing the bias. Every time we change classes, we are changing the bias on the amplifier. Class D is much like Class B. We typically do not bias the stage. The waveform itself, the square wave itself, turns the devices on and off. We know that we have to have forward bias on these transistors for Class A and for Class AB. Now for Class E, push-pull, we have to put the delay in, of course, but it works exactly the same as the other push-pulls. And you get all of the benefits of push-pull with push-pull Class E. Here's a practical example of a push-pull Class E amplifier. And now we have taken the inductors and we've brought them into the center tap coil, simplifying the circuit. So I thought, hey, why don't I take a transistor off one of those ATX power supplies and see if I can do a Class E final with a bipolar transistor. So I grabbed one. It's a 2SC 3150. And I'm looking at the specs, and it looks like it's, wow, very high voltage. It's really a high voltage part, 800 volts at 3 amps. It has 60 picofarads of output capacitance, and it has an FT of 15 megahertz. Wow, that's a little bit limiting. So probably not a good choice for a Class E final. Probably should have a transistor that has an FT, that's at least in the 100 megahertz range or higher. And it doesn't have a lot of gain either. If you hit it with the switching pulse, I'm sure it'll do something. But one thing we have to be really careful with bipolars compared to FETs. We talk about the FETs as having very high capacitance. Typical capacitive reactances could be in the 40, 50, 60 ohm range. And we know that our little driver was driving a 47 ohm resistor quite nicely without any trouble. However, it probably would not be too happy trying to drive a 3 ohm or a 4 ohm or a 10 ohm input of a bipolar transistor. So as a precaution, the first thing that I've done with this particular circuit, which looks a little bit complicated to you guys, so I'll go through it slowly, is I've got a 4-to-1 transformer right up front. In other words, we're coming in at 50 ohms, let's say. It's going to transform that down to around 12 ohms. That's just a safety thing, because if you try to drive a really low load, you're going to pop these two FETs on the driver. So we do have to do some impedance matching in order to go into the very low input impedance of the bipolar transistor. I haven't got much going on the base. I just have a 220 ohm resistor and a ferrite bead to ground. I have a 1 millihenry choke, and it's not even a very good choke. It's just one of those little pot cores. Then I have the Class E network, which is a shunt C, Series L. So at this point, I have a fairly low impedance. This thing was asking for, something like a 10 ohms at this point to make it go into Class E properly. So I have another one of those 1 to 4s, this time the other way. It goes from low to high, hopefully bringing me back up to 50 ohms here. And this network is just simply the harmonic filter. So I hope you all caught that. Looks like a lot of parts, but let's see what happens when we turn this thing on. Will the driver be able to drive this old ATX power supply switching transistor, the bipolar? So we'll turn her on and bring up the voltage to around 15 volts. And my God, it's hard to believe, but the meter did move. We're putting out almost 2 watts. So I would not call this a victory, because we're drawing half an amp at 15 volts. That's around 7 watts input. Give a watt to this, 6 watts input. And we're only getting 2 watts out. That's not very good efficiency. So I don't think the 2SC 3150, right out of the ATX power supply, is a great way to start with our Class E experimentation. Okay, whoa, settle down, guys. This video is taking too long. I'm going to have one more video on Class E. We're going to get there with the circuit, so stand by. Class E Part 2 coming up.